Okay, so what is the Jacobian? It's a fancy way of saying the gradient of a quantity. So Jacobian. So I mean, let's write it this way. Let's say f. Okay, f is a function of functions. So f is a f is a vector of functions. So f1q, f2q, f3q, and so on till fm. Okay, this is vector. I should make it so bold faced so that it's basically a vector of functions. Q is also a vector. Let's say Q is x1, x2, so on till xn. Okay, so what is the Jacobian? It's basically the rate of change of f with respect to q. So what sits on top is a vector, m elements in the vector, and what sits down is also a vector. So how do you compute a derivative of a vector to a vector? Well, that's the Jacobian. What you'll do is you'll do df1 dx1. So I took the first element and I took its partial derivative with respect to x1. If you've forgotten partial derivatives, when you take a partial derivative of any quantity with respect to, say, x1, you think of x2, x3, x4, and so on as constants. You will do nothing with them. You'll treat them as constants. We'll see an example in a bit. And then df1 dx2, so on till df1 to dx n df2 dx1 df2 dx2, so on. Yeah, I keep doing that till I reach dfm dx1 dfm dx2, so on till dfm dxn. Yeah, so you see that it has essentially how many rows? x1, f1, f2, f3. So m rows, right? Because it goes from 1 all the way to m. And then because it goes from x1 all the way to xn along the columns, it's m cross n. So m rows, n columns. So if you do df dq, it's going to be m rows, n columns. F is a vector of m, and q is vector of n. Okay, let's do an example and stop. Here is an example of how to do this calculation. F is x square plus y square, 2x plus 3y plus 5. Q is x comma y. So if you want to do df dq, then it's going to be, think of this as f1, this as f2. So df1 dx, df1 dy, df2 dx, df2 dy. So that is going to be, so the derivative of f1 with respect to x is 2x. You treat y as a constant. df1 with respect to y, this thing with respect to y is going to be 2y. Then f2 with respect to x, differentiate f2 with respect to x, treat y as a constant. So if that will be 2. And df2 dy is going to be 3. Okay, so that is the derivative. If you want to find what that derivative is at 1, 2, so x is 1, y is 2, then that would be substituting the value of x as 1, y as 2. So 2, 2, 4, 3, right? Since I have 1 minute, let me just show you the code on how to do this, which will take less than a minute. Okay. If you can see the screen. Okay. So this is an introduction to symbolic toolbox. You can actually do this differentiation using the symbolic toolbox. You need a SymPy is a package which does symbolic calculations. So here we have x squared plus y squared, 2x plus 3y plus 5, same as what I wrote down. I define xy as symbols. So it's saying that x and y are symbolic, and real is saying that they're real, not complex. So what I do is f equals f1 x comma y. It's basically calling this function, which basically has the symbolic stuff. Z is x comma y, and to compute there is a function called Jacobian. So I say f dot Jacobian z basically computes df dx, where x is, well, in this df dq, where q is z. So running this, you'll see the output here. The matrix is 2x, 2y, 2 and 3, the same thing I wrote down. And then if you want to sub in the value 1 and 2, this is how you do it. It basically gives me 2, 4, 2, 3, the same thing which I wrote down there.